Welcome back to the AI and GIS Frontier podcast. I am an AI researcher, and today my fellow AI researcher and I are diving into Geo Foundation Models, the massive pre-trained AI systems that are reshaping how we work with satellite and geospatial data. Thanks for joining me today.
Happy to be here. As AI researchers, we get to see these developments unfold in real time. And this is probably the single biggest shift in geospatial AI that I have tracked in my career. The pace right now is incredible.
Let us start with what these actually are, because I think a lot of GIS professionals have heard the term foundation model, but are not sure how it connects to their day-to-day work.
Fair question. A foundation model is a large neural network pre-trained on massive amounts of Earth observation data. Think millions of satellite image patches from Sentinel, Landsat, and commercial providers. Once trained, you can fine-tune it for a specific task with very little labeled data. Here is why that matters for a working GIS analyst. Say you are a forester, and you need to map tree species composition across a new timber concession. Traditionally, you would spend weeks collecting ground truth data and training a custom classifier from scratch. With a foundation model like Prithvi, you might need 50 labeled samples instead of 5,000, and you can have a working model in a day instead of a month.
That is a massive workflow change. Tell us about Prithvi specifically.
Prithvi came out of a collaboration between NASA and IBM, and it is fully open source. They have already released fine-tuned versions for flood inundation mapping, burn scar mapping after wildfires, and multi-temporal crop classification. But what is really exciting is how the forestry community has picked this up. Teams are fine-tuning Prithvi for forest disturbance detection, using it to identify illegal logging activity from Sentinel-2 time series. The Canadian Forest Service has been exploring these models to map post-fire regeneration patterns across boreal forests, which is a task that used to require years of manual photo interpretation.
And Google is doing something different with their geospatial reasoning initiative?
Right. Google Research is combining foundation models with generative AI so you can actually reason about geospatial data, not just classify pixels. For a practical example, imagine you are an environmental consultant and a client asks, "Show me all areas within this watershed where forest cover declined by more than 20% in the last 5 years, and overlay that with soil erosion risk." Today, that is multiple steps in ArcGIS or QGIS: loading data, running change detection, clipping, overlaying. Google's vision is that you describe the analysis in plain English, and the system chains together the right foundation models and analytical steps automatically.
What about the European Space Agency? What is their angle on this?
ESO has their foundation models for climate and society initiative, and they are tying it directly to policy applications. Ice monitoring in the Arctic, drought assessment in the Mediterranean, flood zone mapping across Europe. What is particularly relevant for environmental professionals is how they are connecting these models to the Copernicus data ecosystem. If you work with Sentinel data, which most environmental GIS shops do, ESA is building foundation models that are native to that data. No more wrestling with pre-processing pipelines to get your imagery into the right format for a model that was trained on something completely different.
Let us talk about what this means for someone sitting at a desk running ArcGIS Pro or QGIS every day. How does their workflow actually change?
It changes in 3 big ways. First, the data preparation burden drops dramatically. You spend less time collecting training samples and more time on the actual analysis and decision-making. Second, you can tackle problems that were previously out of reach. A small forestry consulting firm can now do the kind of large-scale canopy height modeling or species classification that used to require a team of remote sensing PhDs. Third, and this is the sneaky one, it changes how you think about projects. When building a model is cheap and fast, you start asking different questions. Instead of 1 land cover map per year, why not monthly? Instead of classifying 5 species, why not 50? The bottleneck shifts from model building to interpreting results and making decisions.
Can you give us a concrete forestry example of this in action?
Sure, there is a project in the Pacific Northwest where a timber company is using a fine-tuned foundation model to monitor selective harvesting compliance across their holdings. They feed in bi-weekly planet imagery. The model detects individual tree removals and compares them against the approved harvest plan in near real time. That used to be a job for field crews driving logging roads. Now, one analyst with a laptop can monitor 100,000 hectares. Another great example is in Brazil, where researchers fine-tuned a foundation model to detect early-stage deforestation in the Amazon, catching clearings as small as half a hectare within days of them appearing. That kind of rapid detection was not possible with traditional supervised classification approaches.
What about on the environmental monitoring side?
Wetland mapping is a perfect use case. The U.S. Fish and Wildlife Service has been exploring foundation models for updating the National Wetlands Inventory, which is a task that has historically been incredibly labor-intensive. With foundation models, they can process Sentinel-2 time series to capture seasonal wetland dynamics, identifying ephemeral wetlands that only exist for a few weeks in spring. On the water quality side, teams are using these models to detect harmful algal blooms across hundreds of lakes simultaneously, something that would have been a separate modeling project for each water body just a few years ago.
There are some ethical concerns being raised about these models, though. Nature Machine Intelligence published on responsible geospatial foundation models. What should practitioners be aware of?
The biggest practical concern is geographic bias. If a model was primarily trained on data from North America and Europe, it might perform poorly in tropical forests or arid landscapes. I have seen research where a model that beautifully classified temperate forest types completely failed on mangroves. There are also data provenance questions and dual-use concerns. The same model detecting deforestation for conservation could theoretically be used for surveillance. The Nature paper argues we need governance frameworks built into the development process, and from what I have seen in the research, that is absolutely right. The key takeaway for any practitioner is always validate these models in your specific geography and ecosystem before trusting the outputs for decision-making.
Where do you see this going in the next 12 months?
3 things. First, convergence. We will see unified models that handle remote sensing, weather, and terrain data together. So a single model could tell you about forest health, fire risk, and soil moisture in one pass. Second, edge deployment. Smaller versions of these models running on drones and field tablets, so a forester doing a cruise can get AI-assisted species identification in real time without cell service. Third, the integration with large language models means you will be able to query a satellite image archive in plain English. Ask your GIS system to find all clear cuts within 5 kilometers of a salmon stream, and you get an answer, not a tutorial on how to build the analysis. That is coming fast.
That paints an exciting picture. It sounds like the barrier to entry for sophisticated geospatial AI is dropping fast, and the people who will benefit most are the practitioners doing the actual work. Thanks so much for breaking this down with me.
Absolutely, and I would encourage every GIS professional to start experimenting with these models now. The learning curve is much gentler than traditional deep learning, and the payoff is enormous. This is the kind of shift that happens once in a generation.